Hello everybody, today I'm going to show you how to uh, represent a function f of x using Taylor series. So if you have a function f of x, as long as it's continuous, differentiable on an interval of convergence surrounding a number c, as long as the constant belong to a real, the topology of the real number, we can represent f of x as this following equation. So you have f of x sigma n start from 0 go to infinity, f to the derivative of n at c over n factorial times x minus c to the n power. So that is called the Taylor series, meaning that if you have any c, the integral convergence surrounding c is any real number, but beside that, you have the special case where c is equal to 0, and we call that a Maclaurin series. So with c equal to 0, we can represent f of x equal to the sigma notation, n start from 0 go to infinity, n to the derivative to the nth derivative at 0 over n factorial times x to the n power. You can think of this as just x minus c, but since c is 0, so x minus 0 is just x. So that's why you have x to the n. So if we expand this equation, expand the sigma sign, you can have f of x equal to f to the 0 derivative. It's just what does it mean to have an x to have an f to the 0 derivative? It means just f itself. So f itself at c equals 0, so that f 0 over 0 factorial, and we know 0 factorial is 1. So this term right here would just be f at 0. So that's one way you can write it. And of course, x to the n is 0, so x to the 0 power, that's just 1. So you move on to the n equal to 1, n equal to 1, that f, first derivative at 0, 1 factorial, that's 1 factorial here, x, n is 1, so x, so it's just x itself, plus f to the second derivative. This notation means that the f and then the upper parentheses with a number 2, and it's just a second derivative of f at 0 over 2 factorial times x squared. Okay, n is 2, so that's x squared. Same thing with this one. So you keep expanding out. That's the sort of like a normalization whenever you see a question that require you to find to represent a function f of x using the Maclaurin series, you automatically think of c as being 0. So you remember this equation and replace the c with 0, and there you have this formalization, and then we're gonna plug things in, sort of saying that casually, but we just have to plug in what are the values when we take the derivative of f to a certain degree of derivation. So next I'm going to show you guys how to find, how to represent a function inverse tangent of x using Maclaurin series. So we have the function f of x equal to the inverse tangent x. So here's the function that we need to find. We need to find the series representation of it using Maclaurin series notation. So with the Maclaurin series, we know Maclaurin series is just a special case of Taylor series when c equal to 0. So when c equal to 0, we just know that c equal to 0, x minus c, that's x minus 0, so x to the n. So you have this formalization. Okay, so let's go ahead and find its first derivative of f of x. F of x we have here is inverse tangent of x. So the derivative of inverse tangent of x is 1 over x squared plus 1. And derivative of f at x equal to 0, that is f prime 0, and we plug 0 in here, that's 1 over 1, so we have it 1. So whatever, because we have the formalization here, so it means that whatever the C number is, this applies to Taylor series as well. If you have any C number, as long as it's real, you can just plug in this derivation and you find the value of it as the equation shows. Okay, so now let's take a second derivative. What's the second derivative of 1 over x squared plus 1? That we can treat this as a power function, meaning we can see this as x squared plus 1 to the minus 1. So taking derivative of that, we'll just add up minus 1, so that's why we have a square down here in the denominator. And since we've got to use a chain rule, because inside this bracket there's an x squared, so that's why it is 2x. And since here is minus 1, that's why we have a minus sign in front. F, the second derivative at 0, we plug in 0, x is 0, so that's why it's 0. So we go ahead and find the third derivative of inverse tangent of x. So we can treat this this product here as two entities. So we can treat this particular product, we can think of this as just 1 over x squared plus 1 squared times minus 2x. So this turned out to be a product between two functions. Now we're taking derivative of that, so that means we're going to use the product rule. So we take the derivative of this. This is minus 2 here, so that's why we got to have a minus 2. Alright, so I'm sorry, so we got to have the minus 2. Here is x squared plus 1 to the third, because this is minus, we can think of this as just x squared plus 1 to the minus 2, and derivative of that is just minus 2 minus 1, so that's why it's minus 3, and then minus 2 in front, minus 2 here, so that's why we have the minus sign cancel, we have 4, and since the x squared, right, we did the chain rule, so that's why it's 2x. Okay, so that's why we have 4x times 2x over x squared plus 1 to the third. Okay, for this one, we hold this function, and we derive this function. So when we derive this function, that's minus 2. Okay, same function, keep it the same. So that's why it's minus 2 over x squared plus 1 to the second power. So we plug in x equal to 0 in here. There's no x in the numerator. That's why it's minus 2. Here there's x, so x is 0. Plug in this term right here is equal to 0. That's why the third derivative at 0 of f equal to minus 2. So we'll go ahead and take another derivative of f to the fourth derivative. It's pretty much tedious to do this whole process again, because this is again another a product between x squared and 1 over x squared plus 1 to the third. But we can go ahead and ignore this side, because when we derive this term, the x component will show up, and when we plug in the value, the 0 value, that whole side going to be 0 anyways. So we can go ahead and not care about that for simplicity. So that's why there's a dot there. But here you don't have the x component. That's why when you take the derivative, that's an x that showed up because of the x squared. So again, you plug in 0, that's 0, that's why f to the 4th 0 equals 0. Okay? So, with that being said, if you keep doing that, you keep taking derivative, and you will have, and plug in the value of 0, you will have the values to plug in for this formalization. So we talked about this. We can represent this with a formalization, right? This thing equal to f 0, 0 plus f1 over 1 factorial at 0 x plus plus plus, and it's just going on, right? Again, f to the second derivative at 0 over 2 factorial x squared. So if we keep doing that, and we end up having inverse tangent of x equal to x minus 2 over 3 factorial x to the third plus 24 over 5 factorial times x to the fifth minus, and you keep going on. And you can go ahead and simplify this. 2 over 3 factorial, that's 1 over 3. 24 over 5 factorial, you know that 4 factorial, that is 24 equal to 24. So this is like 4 factorial over 5 factorial, that's just 1 over 5. So 1 over 5 x to the fifth. And then you see the pattern here. You see the power of x. This power is 1, this power is 3, and this power is 5. So it's an odd number, increasing odd number. Same here with the denominator. Here, down here is 1, down here is 3, down here is 5. So the same. The value in the denominator and the power are the same. And you know that when you represent an odd number is 2n plus 1. And depends on where you start. N can start at either. N can start at 1, at 0, at 2, at any numbers that you want. It's just an index. But as soon as you choose a certain number for n to be started with, you gotta be consistent with the formation and the pattern. So here I choose n to be equal to 0. So if you so n equal to 0 here start at 1. So that's why it gotta be 2n plus 1, right? The power of x is x to the 1, so that's why it's x to the 2n plus 1. Because n starts at 0, n plug in 0, 2 times 0 plus 1, that's 1. 2 times 0 plus 1, that's 1. So it's consistent. And n to the minus 1 to 0, that's 1 as well. So that's why it's consistent. You can go ahead and check one more time. N equal to 1, plug in, that's minus 1. 1 in here. 2 plus 1, that's 3. 2 times 1 plus 1, that's 3. So x to the cube. Again, and the 2 to the fifth and 1 to the fifth. So this is the Maclaurin series representation of the function inverse tangent of x. And the interval of convergence for this particular function is from minus 1 x to 1. Okay, this is the interval of convergence. How you go about and find this? You can either apply the root test or you can apply the ratio test and set it to be less than 1, and you can find the appropriate value for x in order for this series to converge. Thank you very much.